Okay, identify and exploit symmetries of the unit circle. The further down in math you go, the more symmetries you can find, the better, because it saves you a whole lot of thinking a lot of the time. So, what's a unit circle? Here is a unit circle. Unit circle is, unsurprisingly, a circle centered on the xy plane, so the Cartesian plane at 0, 0. It has a radius of 1, hence the name unit circle. 1 unit, it's a circle. So we've got 1, 0 over here, negative 1, 0 over there, 0, 1 up here, and 0, negative 1 there. Now I'm arbitrarily going to decide that the circle starts here and it goes counterclockwise around. Now you are free to be really annoyed about that, but unfortunately that's how the convention started and that's how we're going to have to continue, otherwise life gets really difficult for you. So sorry about that, but that's where a circle now starts from the rest of math life on, and it goes counterclockwise around. Cool, alright. Well, first thing that I want you to do is just type in a couple of things into your CAS, make sure that you're in degrees. Sorry, into your calculator I should say. So if I type in sine of 30, I should get out a half. Great. If I type in sine of 30, I should get root 3 on 2, and a whole bunch of other things. Typed up a whole bunch of these. Now, hopefully what you notice is that there's a little bit of funny business going on. Namely, that, hang on, this guy and this guy match, and this guy and this guy match. That's a little bit weird. What's going on there? And then if we keep going around, we go, oh, that's even more interesting. This guy and this guy are getting a little bit close. There's a negative involved now. That's weird. And here he is again. And here's this guy again. And this guy again, just with negatives involved. Something a bit sus. And then this guy turns up down here with a negative. This guy turns up here with a negative. Something's a little bit suspect. Well, let's see if we can explain this behaviour. I have a very handy-dandy right-angle triangle, and it is at this point that we begin to see that all triangles are merely shadows of circles, and that all of your trigonometry, despite the word the tri in trigonometry meaning 3, it's actually just a shadow of a circle, and it's all been shadows. It's all been circles the whole time. You just didn't know. So, got me there a triangle, right? That would be my opposite, my adjacent, my hypotenuse. Okay. Well, how do I get sine? Well, sine of the angle is always O over H. Okay. Well, that's all well and good. I'm going to do something a little bit weird. I'm going to say that my hypotenuse from now on, I'm just going to pick that that is a length 1. So it doesn't matter how big my triangle is, I can always just go, well, whatever the hypotenuse is, I'm going to declare that 1 unit of some description. Doesn't matter if it's 6,843 millimetres, I'm going to call that 1 unit. And then I just have to resize these accordingly. So I'm always just going to call that 1. Alright, well in that case, this is now, whatever that opposite side is, divided by 1 of these units. Alright, but something divided by 1, that's just whatever that is. So I can think of this entire side here just as representing sine of that angle. That's a little weird. Okay, so what? Well, let's think about the same thing with cos. Cos is adjacent over hypotenuse. Alright, fine. Well, now that hypotenuse is a 1, so I've got adjacent over hypotenuse. So that's just the adjacent. Alright, fine, so this we could think of as cos theta. Alright, good job. Now, you might jump to the conclusion, oh, that means that this is tan theta. Unfortunately, no, that doesn't actually happen. Tan does turn up a little bit later, but not right there. And we know that that happens because this is 1, and tan theta is commonly not 1. So, anyhow, okay, great. Well, why have we got a nice colourful triangle over here? Well, I'm so glad you asked. I have the same triangle here. So if I think of this guy as the purple side length of 1, I'm in a circle with radius 1. So this line has to be that 1 side. Well, that means that this distance here would have to be sine theta. And this distance here would have to be a cos theta. Okay, great. Well, that's interesting. We put a triangle inside a circle. But, lo and behold, this begins to explain some things. Let's imagine now, because I didn't pick whatever angle this was. Right? That could have been any angle, and it works for all of them. That's weird. So, okay, what happens as I fiddle around with that angle? Well, I could make it really small, close to 0, and I could go up to 90, but then if I go to 90, how does that work? Because I've got a right angle triangle here. How can this be a right angle triangle if it's still a triangle? I've got two 90-degree angles in a right angle triangle. That seems a little weird, doesn't it? Or worse yet, hang on, there was nothing saying that this angle had to be lower than 90 other than our drawing. What if I just pushed it? Just see what happens. This is common in math. You just go, I have no idea what this is going to do. Poke. And then your whole understanding falls apart, and then you have to rebuild yourself. Because, lo and behold, if I type into a calculator, what is sine of something bigger than 90? It doesn't just say, well, what's wrong with you? That's not a right angle triangle. It'll actually spit out a meaningful result. So, for example, sine of 120 is root 3 on 2. Cos of 120, negative a half. Tan of 120, this. Hang on. How can that happen? That's gone past. That means I have to have 90 degrees and 120 degrees. What angle is this? Well, that stuff's up your thinking a little bit. But that's because you've been living your entire life in triangles, and you should have been thinking about circles the whole time. So, let's think about it over here. So, let's say, for argument, that this was 60 degrees, just because it looks roughly like 60 degrees. Okay, what if I change my angle now to be over there? So instead of just this purple angle, remember this is always where it starts, I'm going to go around to there. Well, that's a little bit weird. Now, conveniently, you'll notice I've made this a perfect mirror image. Well, that means that this angle would have to be the same as that angle. Okay, well, that would also mean that this cos distance over here would be the same distance as that. Okay, so I'm going to call this guy different, call him alpha? No, I'll call him theta. Theta in pink. In fact, I'll change that colour just so that's abundantly clear. Cool, so I'm going to change that to pink. So now I've got, this must be cos pink. And by a similar argument, this is sine of pink. Okay, so this is my pink angle. Well, pink plus purple equaled 180. Okay, so whatever this guy was, if I flip that around, I get the same value. So, what am I saying? I'm saying that if I think of, where was 60? 60. Sine of 60. Okay, that's the blue for sine, of 60 degrees is this guy. According to my pictures, that should mean that sine of 120 should be the same. And lo, that's exactly what we get. Well, that's interesting. Well, that's a little bit sus. Well, what happened with cos? Okay, well, let's think of cos of 60, wherever he is, there it is. Okay, and then I want cos of 120. Well, I get a half and, oh, hang on, it's negative a half. Why is it negative? That distance is the same. But hang on, this was positive 1, this is negative 1, because we're on the negative x-axis now. Or the negative side of the x-axis, I should say. This was 0, so we've actually gone into the negative of the x-axis. Well, what does that mean? Okay, so I've ended up with an angle of 120 degrees because one of the sides of my triangles is a negative length. Now, at this moment you go, hang on, you can't have a triangle with negative lengths. That's a little bit ridiculous. What's wrong with you? And fair enough. But the good thing about mathematics is it doesn't care if you're working in the real world or not. It will quite happily just wander off into things that are logically true, but may not be of this world. So we ended up discovering that we can actually talk about these negative lengths. Alright, so I can have right angle triangles that have angles that are bigger than 90 degrees and have negative lengths. Basically, the short answer is, yeah, nothing wrong with that at all. And if we fiddle around a little bit more, we might find some more symmetries. So, let's find another one. Let's say now that I draw down this way. Okay. And at this point I wish I had better colours, but I don't. Well, I'm going to draw this such that this angle in here is still theta. Okay, well this distance hasn't changed at all. And now this distance would have to represent sine of that new side. So that would be, if we can change colours slightly, call this all the way around here. I'll call that alpha, but I'll just talk about it for now. So this distance would be cos of alpha. This distance would be sine of alpha. Okay, fine. Well, if we did beta, or beta, beta, okay, so now all the way around to there, I'm going to call beta. Well, this angle is still theta. Hope I didn't say theta before, like a bogan, but anyway. Cool. So we've got, alright, this distance would be cos of beta, beta, and this would be sine of that beta. Well, this is all looking a little bit odd. This is all getting a little bit messy as well. Well, with sine and cos on there, it's not so bad. What if we now really mess things up and talk about tan? Well, we had sine and cos on these bits. It turns out that tan, unsurprisingly, is short for tangent. Now, where is this tangent? Turns out, oops, I'll put it in block. Put some dotted lines in here, dotted lines in there. I draw a tangent line at the start of the circle. So that line is tangent to that circle right there. Tangent meaning if you get like a tennis ball and you put a ruler on top and you balance it, the point where it's touching is the point of tangency, and the ruler is tangent to the tennis ball. Beautiful. So this line is tangent to that circle at the point 1, 0. Fantastic. Well, it turns out the tangent describes, if I continue that line up, and there's a couple of definitions, but this is the one I'm going to run with, that distance there is tan of theta. Theta. Cool. To draw it on the other side, well hang on, if I continue this on, I'm never going to get over there. So there's a second one coming down that way. Dot, 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 dot. So up that way would be tan of, we're in the pink angle now, pinky. And similar story going down bottoms down there. Alright, so that'd be tan of alpha, tan of beta from before. Okay, well this is really starting to get quite a busy diagram. Is there a way that we can shorthand a bit of this sort of thing? Well, what I would have you think about is, well, what's sine doing over here? Sine starts really small and gets progressively bigger and bigger. And over here it gets smaller and smaller. Goes under here, well now it's below, so the y value is going to be negative. So sine is negative here, it gets more and more negative, and then gets less and less negative, and we're back to 0. Okay, so sine was positive here, so I'll put this in for now. Sine was positive here, sine was negative there, sine was negative there. Okay, what happens to cos? Well, cos starts off wide. As the angle goes around, the base of that triangle gets skinnier, 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 goes into the negative, so it's negative up here. Go, still negative, comes back in, spins around, now it's back to positive again. So cos was positive here, was negative here, positive here. Alright, what happens with tan? Well, tan, okay, it's going up here, it's positive, positive. Now at this point, I would have us think, because it's like, well, hang on, I've gone off to infinity. Does that mean that I start back at infinity and work my way down? Or does that mean I've gone past infinity, how do I come back from that? Because I never actually reach infinity. So it's a little bit weird. So at this point I get you to remember tan theta is equal to sine theta over cos theta. If you don't know why, that's fine. Sine is O over H. Put it right in there. Cos is A over H. fraction divided by a fraction, those bottoms are going to cancel out. So we get O over A. But that's tan. So sine over cos must equal O over A, but O over A equals tan, therefore tan must be sine over cos. So conveniently, positive sine divided by positive cos, positive over a positive, that should be positive. So tan must be positive here. That's great, well that makes sense. Sine is positive, but cos isn't. So a positive divided by a negative, oh, tan would be negative there. So this actually starts off very negative and comes down. Okay, and as you may guess, it goes positive here because sine is negative here because there's nothing there. Cos is negative here, negative divided by negative, that becomes positive. So this is tan getting more positive. Cool. Cos is positive here, but sine is negative. Negative divided by positive is negative, so tan's negative in there. Okay, well, I've got SET, STC. Well, these are pretty good because they're just one letter. Sine is the only one that's positive there, tan is the only one that's positive there, cos is the only one that's positive there. Rather than writing all three, I'll just write A for all of them. So they're all positive in there. Everyone's happy. Okay, great. Well, I really don't want to have to remember, like, go through all of that process every time. So maybe there's a shorter way, and there is. We can just remember this ASTC. You are welcome to remember that however you see fit. I recommend the way that I was taught in Year 10 by Ms. Bobber, ages and ages ago. All students talk crap. It's true then, it's true now, easy to remember. So ASTC, don't care how you remember it, just as long as you associate them with the correct quadrants. Incidentally, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. You go around in that same order. Beautiful. Okay. So from that, we should be able to predict these other ones as well. I recommend that you just clarify for yourself where those numbers do actually come out from this. There are a couple of other cool little tricks that we can do as well. So, if we say things like sine of 90 minus theta, I don't know what theta is, how am I supposed to do anything with this? Well, I can think about it. So I can say, okay, my unit circle, I'm just going to draw the first quadrant for this. Okay, 90 would be up here, this would be 0. And I have some angle theta. Okay, but it's 90 minus theta. So this angle in here would be theta, so I've got 90 and then I'm taking away theta down that way. Okay, well, I want sine of that. Okay, well, remembering that sine is the vertical. So that's sine of that. But, okay, if I think about this for a second, that's the same as that. That's the same as that. Well, rather than describing this in terms of this weird angle, I could think of it in terms of this angle instead. Okay, well, I'm going to call this something else. We'll call it alpha. Alright, well, that would mean that this side, which is cos, hang on, cos of, is that what I wanted in the end? I've forgotten. Over h. Which one did I want? Sine of this. Sine is this. So I want that. Okay. So this side, sine of this is those dots. Rather than describing it as this weird combination of things, I can think, hang on, I just want to describe this. Well, that's the same as this. So if I redraw that triangle, there, with green dots over here, and blue dots over here, purple angle in between, we know that this hypotenuse is 1. Alright, well I want this side, that would be the opposite, so I can describe this as cos of the angle theta, because O over H, O over H, what have I done? Sine, O dear. Did I solve that? Hang on. Have I done that? Sine of this should be cos of this, yes. Yeah, over this, I wanted that. How did I do that? I want this height, so this is, oh sorry, I want this green, blue, there it is. I want this blue height, because that's what sine represents, the blue height of this with angle. So what I want is, I'll call this x, to stop forgetting things. I want that x. Okay, so this equals x, which equals cos, because I've got the adjacent over the hypotenuse. Sorry about that. Beautiful. Okay. Other one. Just because we can. Okay. Cos of negative theta. Now, I'm going to do this just like I did this. I'm going to assume that the thetas are acute angles, just for simplicity. It'll work more generally, but we'll just do simple short things because we're only in year 10. Okay. There's my, ooh, terrible. No, not happy with that. Try again. It's not the best work ever, but that'll do. About there. Okay. So we'll go. Yes. Cool. Let's say that that's positive theta. That's negative theta. Remembering from before that positive goes this way, negative goes that way. Okay, fine. That distance and that distance would be the same because I'm moving off by the same amount. Okay, fine. Well, did I do the right colours? Yes, that's fine. Cool. Alright, well, what do we see here? Well, these distances are going to be the exact same. So that means cos of negative theta, which is this distance, is the same as cos of positive theta. So that's all well and good. And you can extend both of these arguments through the rest of the quadrants if you so see fit. Definitely prove to yourself that that happens. For now, it's not 100% that we need to be dealing with this, but it just shows you that regardless of what the angle is, you can start making these changes to make life a bit easier for yourself. Get rid of negatives and such. That's that. Beautiful. So that's 4i. For now, we're leaving everything in degrees. Next time we'll start to change it to make it better for eventually for calculus. But for now, it's just about recognising all these triangles. We're just hidden inside this bigger circle. So far, you spent all your life in just this first quadrant where all the lengths were positive. Now we're allowing for things to have negative lengths, which means that our angles can be whatever we want. And that means that we can shortcut things because we don't have to, every triangle in here just gets replicated over here just with negatives floating about. So we can take a couple of shortcuts. So 4i, that's that. I expect that you'll have questions, which is fine. Do email me and I'll see you on Monday or Thursday, depending on when you're watching this. Okay, bye.